Hello and welcome to Quantum Bridge, a program designed to introduce students to the world of quantum physics. In order for you to understand quantum physics, you will need to know some concepts that will be taught to you over the next videos. This video will cover basic trigonometry, complex numbers, and Euler's identity. We will begin with trigonometry, the study of triangles. This is a right-angled triangle, meaning a triangle with one angle of 90 degrees, marked by the sign we see in the lower left corner. We have sides labeled A, B, and C. Importantly, the side labeled C is the hypotenuse, the longest side of the triangle, and is opposite the right angle. Let us take a moment with the shape in front of us. We have two squares made up of the triangle we saw before. A plus B squared is the area of the larger square because its side lengths are A plus B. The inner square simply has an area of C squared. However, we can also get the area of the inner square by subtracting the area of the triangles from the area of the larger square. A plus B squared minus 4 times 1/2 times B times A for the 4 triangles equals C squared. When we expand, we get A squared plus B squared plus 2AB minus 2AB equals C squared. A squared plus B squared equals C squared, also known as Pythagorean theorem, although it was not discovered by him. This formula allows you to calculate any of the other sides of a right-angled triangle if you know the other two. Next, we're going to learn about some trigonometric functions. A function in math is something that takes an input and returns a single value. There are 3 basic trigonometric functions: sine, cosine, and tangent. You will also sometimes see these abbreviated as such. And these functions take an angle as an input, denoted by theta, and output a number. Let's get a triangle for visualization and label our sides and an angle, theta. Using the theta in our triangle diagram, the sine of theta is equal to the length of the side opposite theta divided by the length of the hypotenuse. In other words, B over C. The cosine of theta is the length of the side adjacent, which means beside, to theta, divided by the length of the hypotenuse, so A over C. The reason it's not C over C is because adjacent usually refers to the non-hypotenuse side, and C over C wouldn't make for a very good function. Finally, tangent of theta is equal to the length of the side opposite theta divided by the length of the side adjacent to it, therefore B over A. An easy way to remember these functions is with SOHCAHTOA, which tells you that the sine is the opposite over the hypotenuse, cosine is the adjacent over hypotenuse, and tangent is opposite over adjacent. There are inverses of these functions, which simply do the same thing in reverse. So inverse sine takes opposite over hypotenuse as an input and returns theta. Inverse cosine is adjacent over hypotenuse, and inverse tangent is opposite over adjacent and returns theta. The unit circle is a great and simple tool. A circle with a radius of 1. With the unit circle, angles are discussed with reference to the positive side of the x-axis and counterclockwise. Right now, we have a point on the circumference of a circle, which is 45 degrees above the x-axis. If we create a triangle with our line, we see that the height of our triangle, also the y coordinate of the point on the circle, is equal to the sine of 45. Opposite, which is y, and hypotenuse, which is 1. Likewise, the x-coordinate of the point on the circle is the cosine of 45. The tangent of 45 is y over x, which is sine 45 divided by cosine 45. This shows us that in general, the tangent of theta is equal to sine of theta divided by cosine of theta. You can show this algebraically like this. Remember, sine is equal to opposite over hypotenuse, and cosine is equal to adjacent over hypotenuse. Dividing these two and flipping cosine gives us opposite over adjacent, which is tangent. Imagine we were to rotate this point until it was on the y-axis. The height will also be equal to the radius. Therefore, the sine of 90 is equal to 1. And since this point is directly on the y-axis, it has x-coordinate of 0. The cosine of 90 is 0. However, now the tangent of 90, being sine of 90 divided by cosine of 90, is now 1 over 0, which is undefined. Furthermore, we'd have the same problem if we were to rotate another 180 degrees to an angle of 270 degrees, with tangent of 270 is equal to negative 1 over 0, which is undefined. If we start at 0 and rotate until we arrive at the same point, we now have an angle of 360 degrees. If we kept going we would have 361 degrees, etc., but the same cosine, sine, and tangent values as 1 degree. This shows us that these trigonometric functions are periodic, meaning that their values repeat after a given interval, in this case, 360 degrees. Lastly, going clockwise instead of counterclockwise simply gives us negative degrees. For example, going clockwise by 10 degrees instead of 350 degrees counterclockwise are the same thing. This clockwise motion is represented by a negative sign. So negative 10 degrees is 350 degrees. This is the completed first quadrant of what the unit circle usually looks like. X and Y coordinates, and therefore cosine and sine values, written in brackets. There are also fractions of pi written with the angles in degrees. This is another way of measuring angles known as radians. If we imagine a circle with a sector with an angle and an arc length, the side lengths of the circle are the radius. And given that the circumference of a circle is 2 pi r, dividing by 360 gives us an expression for the arc length of a sector, given by the radius and the angle. What if the arc length was also the radius? Well, knowing that the circumference is 2 pi r, we'd only be able to fit 2 pi sectors into the circle, and therefore 2 pi of the angle that created the arc length of the length of the radius. This angle that creates a sector with an arc length of the radius is 1 radian. Therefore, 2 pi radians is equal to 360 degrees. For example, if we wanted to convert pi over 6 radians into degrees, dividing by 12 on both sides leaves us with 30 degrees. I leave the rest of the circle to you as a challenge to fill out using the same intervals as the first quadrant. Complex numbers, written in the general form a plus bi, where a and b are real numbers and I is the square root of -1. The real part of a complex number is the a and the imaginary part is the b. They're not made up numbers, and they have an important use in math, physics, finance, and etc. Addition with complex numbers is simple. For example, 7 plus 12i added to 9 plus 3i is simply 16 plus 15i. Similarly, subtraction functions as expected. "17 plus 4i minus 12 minus 6i We expand and account for the negative, giving us 17 plus 4i minus 12 plus 6i, and 5 plus 10i. Multiplication with complex numbers is also simple. 4 plus 3i times 44 minus 6i gives us 176 minus 24i plus 132i minus 18i squared. Let's combine our terms with the I. Remembering that I squared is equal to negative 1. And finally, 194 plus 108i. Division of complex numbers requires us to know of the complex conjugate. The complex conjugate of a complex number 2.5 plus 3.5i is 2.5 minus 3.5i. In general, the complex conjugate of a plus bi is a minus bi. This is useful when you multiply them together. And we get a squared minus abi plus abi minus b squared I squared, which becomes this, and a squared plus b squared, which leaves us with no imaginary part, as in no part with I in it. Now that we know what the complex conjugate is, we're ready to divide. 4 plus 2i divided by 2 plus I. Let's multiply the top and the bottom by the complex conjugate to get rid of the I. And we're left with 2. Next, we will learn to graph complex numbers as vectors. A vector is a quantity that has a magnitude or size and a direction. This type of graph is called the complex plane because it has real numbers on the x-axis and imaginary numbers on the y-axis. For example, this vector has a length but also a direction away from the x-axis. The vector can be described in terms of those values or also as 3 plus 3i. To add vectors, for example, the black and orange vectors, we line them up tip to tail, and then the sum is the new vector that we draw from the tip to the tail of the other vector. Also, the direction of addition doesn't matter. We could have lined the black vector up tip to tail, drawn our sum vector, and it would still be the same vector as the other way. To subtract vectors, for example, black vector minus the orange vector, we rotate the orange vector by 180 degrees to obtain its negative. Because when you're subtracting vectors, you're really just adding the negative. After rotating the vector by 180 degrees, we simply add as normal. To find the magnitude of a vector or complex number, let's make it into a triangle with its x and y coordinates. Using the Pythagorean theorem, the magnitude squared is equal to 3.5 squared plus 2.5 squared. $12.25 plus 6.25 and eventually we have that the magnitude is approximately 4.3. Another way to find a complex number's magnitude is to use its complex conjugate. Remember that when we multiply by a number's complex conjugate, we get a squared plus b squared. Taking the square root of this also gives us the magnitude. What if we wanted to use the magnitude in angle to describe the vector instead of x and y coordinates? Using the angle of the vector with the x-axis, sine of theta is equal to the y-coordinate divided by the magnitude. This absolute value symbol is used to denote magnitude of the vector v inside it. And the arrow on top of v tells us that v itself is a vector. We have that the magnitude times the sine of theta is y. Cosine of theta is equal to the x-coordinate divided by the magnitude so magnitude times cosine of theta is equal to the x-coordinate. However, because our y-coordinate is the imaginary part because it has that I, we must also add our factor of I. Now we can write our complex number as the magnitude times the cosine of theta plus the magnitude times I times the sine of theta, a plus bi. Factoring out the magnitude leaves us with magnitude times, then brackets, cosine of theta plus I sine theta. Lastly, what if we had the sides but wanted the angle? Well, tangent of theta is equal to 3.5 divided by 2.5. So inverse tangent of 3.5 divided by 2.5 is theta, which is about 54.5 degrees. This form of representing complex numbers using magnitude and the angle is called polar form. Finally, we're going to learn about Euler's formula. Many of us have heard of Leonhard Euler and his irrational number E, which is about 2.718. Importantly, e to the power of I times theta is equal to the cosine of theta plus I sine theta. Remembering the polar form from last section, multiplying both sides by magnitude, we can arrive at the same form. The complex conjugate of e to the power of I times theta is e to the power of negative I times theta. So that would be equal to cosine of theta minus I sine theta. So our previous vector can be written as 4.3, which was the magnitude, as e to the power of I times 54 degrees. Which should be 4.3 times cosine of 54 degrees minus I sine 54 degrees. This is known as the Euler form for complex numbers and allows us to take advantage of exponent rules with complex numbers. Next video will discuss more on vectors and matrices. Thank you.